Solving a three-dimensional wave equation using Dirichlet conditions.
Dirichlet! The wave equation is an important PDE used to describe, you guessed it, waves. It arises in fields like acoustics, electromagnetics, and fluid dynamics.
What are the Dirichlet conditions?
Science?
Unlike Newman conditions, which specify the flux through the boundaries, Dirichlet conditions specify the exact value of the equation at the boundaries. For our equation, we set this equal to 0.
The wave equation can be used to calculate many things, but it's mostly used to calculate wave propagation through three-dimensional curved solid objects, like cymbals and drums.
Good morning, and today I'm going to walk through a 3D wave equation with Dirichlet conditions. So first off, we are given a wave in 3D bounded along the x, y, and z axes at g, y, and I. And this is a Dirichlet boundary condition problem because we are given that the u at certain points is 0 and that the initial conditions are some function of x, y, and z. Now, as mentioned before, the wave equation itself is of the form utt is equal to k squared times the Laplace squared of u, which can be rewritten then as this function here. Now, the solution we're trying to find is of this form, that u of x of y of z of t is equal to some function of x, y, z, and t. Alright, so with that in mind then, it's time to actually set up the problem here. So first off, we can rewrite the actual wave equation as this. And from here, we have to get 4 different equations in terms of t prime and t, x double prime and x, z double prime and z, and y double prime and y. And we can do that just by doing this. Dividing everything by x, y, z, and t, and also the constant k just for the sake of simplicity. This then yields t double prime of k squared is then equal to x double prime over x plus y double prime over y plus z double prime over z is all equal then to some term negative lambda. And from this point here, we can then rewrite these as 4 different equations. The first of which is just t prime plus t lambda is equal to 0. Then from there, looking at this equation here, we can see that x double prime over x is then equal to negative lambda minus y double prime over y minus z double prime over z is then equal to then, again, some constant which we'll just call negative a. And then this can then be rewritten as x double prime plus x a is equal to 0. So from here now, we can actually go in and find the eigenvalues for the function. In this case, I'll be showing you how to find a. So first off, we assume that a is equal to 0, which then, by solving for the characteristic equation, it gives us that x is equal to ax plus b, where a and b are again here just random constants. And then we go in and start subbing in our boundary conditions here. So x of 0 is equal to 0, which is then equal to b. And then again, x of g is equal to 0 is equal to a, simply because b in this case here is 0. So a is not, or 0 is not an eigenvalue then. This is a trivial solution. From here, we move on to seeing if x is less than 0. In this case, we set a equal to negative p squared. This is just a convention we use simply to make our lives easier. And then using this and solving for the characteristic equation, it yields the following. That x is equal to c1 e to the p px plus c2 e to the negative px, where c1 and c2 are again just constants. Using our boundary conditions, we see that c1 plus c2 is equal to 0, and that x of g is then equal to c1 e to the gx plus c2 e to the gx is again equal to 0. And using these two equations, we can show that this is again a trivial solution. Finally now, we have to show that a is greater than 0, and we can simply do that by setting a equal to p squared. Again, that's just for simplification's sake. Using this substitution, then we can find the characteristic equation of this solution to be x is equal to c1 cosine of px plus c2 sine of px, where again c1 and c2 are just constants different from part 2, but constants nonetheless. Applying our boundary conditions yields that c1 is then 0, and then that c2 is a non-zero then. And then in this case here, since this is all equal to 0, we have to find at what value then sine will be 0, because our c2 can't be 0. And this will be 0 when p is equal to n pi over g. So that is our p, and then given this and that, we can say that the eigenvalue for this function then is a is equal to n pi over g quantity squared. So from solving for all of our eigenvalues a, b, and c, we get these three equations here and these three values for the eigenvectors here, here, and here. In this case, you'll see a lot of extra variables that I didn't exactly explain before, so I'll explain those now. In this case, n, m, and l are just the index of that function. That'll become more important after we actually set the equation up in summation form. G, h, and I are again just the boundary conditions, and c, n, c, m, and cl are the constants in front of the equations then.
Go.
So once we've solved for x, y, and z, we can now solve for t, which we call from the setup step t double prime and plus lambda c squared. T is equal to 0, and just for simplicity's sake, I'm going to set lambda c squared equal to lambda naught. So given this, we can then solve for t using the characteristic equation and find that t is equal to b1 cosine root lambda naught t plus b2 sine lambda naught t, which then we apply our initial condition where t prime of x, y, z 0 is equal to 0. So taking the first derivative of t, we find this equation here, and subbing in when t is equal to 0, then t prime is equal to 0, this portion of the function goes to 0, and then we're left with that b2 is then equal to 0. So coming back up to this equation here, that goes to 0, and we're left with that t is simply equal to some constant times cosine of lambda naught t. From before, we see that we were trying to find our equation of u in terms of x, y, z, and t, which we've found x, n, y, m, z, l, and t. So now we just come over here, and we plug all of those equations then into a triple series of sum of L equals 1 to infinity, M equals 1 to infinity, and N equals 1 to infinity. Where this constant here, C, M, and L, can be solved then by applying the second initial condition where U of X of Y of Z of 0 is equal to some function of X. So when T is equal to 0, then this term here then goes to 1 because it'll be cosine of 0 then, which then coming over here, we can see that the constant c and ml is then equal to this exciting looking triple integral, which won't be solved now because we don't actually have a function of x, y, and z. And this then is your final solution. That's your constant, and on this side here is the actual function.